Welcome back to the Lost Tactician. Today we're stepping away from the battlefields to explore a mystery that has puzzled metallurgists for centuries. Imagine a Roman legionnaire's shovel, buried for 2,000 years, unearthed not as rust-consumed rubble, but as a tool that could still bite into soil. Imagine Viking rivets pulled from anaerobic depths, still holding ship planks together with a grip that defies oxidation's relentless pull. How did ancient smiths preserve iron without zinc coatings or modern chemistry? The answer lies in something far more compelling, a synthesis of empirical knowledge, environmental adaptation, and the unwitting leverage of nature itself. Today, we're unpacking the lost science of iron preservation, revealing how ancient civilizations didn't merely stumble upon durability, they engineered it with precision that modern material scientists are only now fully comprehending. This is the story of rustproofing before the age of chemistry, when survival meant understanding the marriage between metal and environment. The fundamental truth is deceptively simple. Iron rusts, it oxidizes, it corrodes. This is thermodynamic law. Iron wants to return to its ore state. Iron oxide is the lower energy state toward which all metallic iron tends, yet across archaeological sites from the Roman Empire to Viking expanses, we find iron artifacts resisting this journey for millennia without a single molecule of modern protection. When archaeologists excavated a Roman carpenter's toolkit from Pompeii, buried by Vesuvius in 79 AD, they expected disintegrated remnants. Instead, they found recognizable chisels and nail fragments still bearing tool marks from their forging. When Viking longship excavations at Oseberg in Norway revealed rivets 12 centuries submerged in anaerobic conditions, metallurgists couldn't explain the preservation with confidence. The rivets showed protective patina, but the degree of preservation exceeded theoretical predictions based on laboratory corrosion rates. This is where our investigation begins, not with theory, but with evidence that ancients possess knowledge we've largely forgotten. The mystery doesn't lie in whether ancient iron lasted. Archaeology proves conclusively that it did. The mystery lies in how they achieved this without chemistry textbooks, without electroplating, without understanding the electrochemical nature of corrosion that wouldn't be documented until the 19th century. To understand ancient rustproofing, we must dismantle a modern assumption that impurity is the enemy. Contemporary metallurgists pursue iron purity as virtue, yet ancient iron produced in bloomeries, primitive furnaces predating medieval periods, was anything but pure. And here lies a remarkable paradox. This impurity may have been iron's greatest defender against corrosion. Ancient bloomeries operated between 1,100 and 1,200 degrees Celsius, sufficient to reduce iron ore into workable metal, but insufficient to fully liquefy it. The result was a sponge-like bloom mixed with gangue, non-metallic waste, primarily silicate-based slag. This slag would be hammered out through exhausting reheating cycles, but complete removal was impossible. Microscopic analysis of Roman iron reveals substantial silicate inclusions distributed throughout the metal matrix. These slag inclusions functioned as barriers against corrosion propagation. Rust, chemically speaking, is iron-ion migration through the metal's crystal lattice in the presence of oxygen and moisture. Non-conducting silicate inclusions interrupt this ionic pathway, fragmenting the electrochemical circuit required for rust to spread. They create naturally compartmentalized structures that limit corrosion's advance. Additionally, the working and reheating of bloomery iron created fibrous grain structures quite different from modern rolled steel, conferring greater resistance to uniform corrosion patterns. Beyond slag, ancient smiths unknowingly manipulated another crucial variable: phosphorus content. Analysis of Roman structural iron reveals phosphorus concentrations sometimes exceeding 3%. In modern practice, such phosphorus would be considered contamination. Yet research examining these artifacts demonstrates that phosphorus, when distributed evenly, contributes to stable protective patina formation, a layer of complex iron oxides and phosphate compounds far less reactive than bare iron. Carbon content presented another variable skillfully manipulated by ancient blacksmiths. Rather than pursuing uniform carbon distribution, many employed differential heating and quenching that created zones of varying carbon content within single tools. Harder regions reserved for cutting edges, softer regions concentrated in shafts. This microstructural variation influenced localized corrosion patterns, protecting critical areas while concentrating corrosion in less essential regions. If metallurgical composition was the first line of defense, environmental adaptation was the second, and perhaps more crucial. Ancient iron preservation depended profoundly on where it was kept. So, moisture and oxygen are, the two essential reactants in corrosion's equation. If you remove either one, rusting just stalls dramatically. Objects that are buried in dry tombs or preserved in desert environments, well, they tend to show substantially better preservation than those exposed to moisture and air circulation. For example, Egyptian tombs containing iron implements survived for millennia with only some surface oxidation. The absence of liquid water, the electrolyte through which corrosion actually proceeds, represents perhaps the most effective passive protection mechanism available. Yet, equally fascinating is the opposite scenario: anaerobic preservation. The Oseberg Viking ship, which was buried in a Norwegian mound sealed from atmospheric oxygen, reveals remarkable preservative power. The ship's rivets were waterlogged yet oxygen-free. In the absence of oxygen, the primary oxidation pathway is blocked. Iron undergoes a different kind of alteration, developing these dark, magnetite-rich layers that are remarkably stable over centuries. These conditions really demonstrate that the ancients, perhaps through experience with shipboard storage in damp conditions, learned, almost intuitively, that saturation with water could actually preserve better than dry exposure, provided air was completely excluded. Soil composition itself played an underappreciated role. Iron buried in alkaline, lime-rich soils, conditions near ancient Roman construction sites where concrete and limestone dominated, develops passive protective layers. The alkaline environment raises pH sufficiently to encourage stable iron hydroxide and iron oxide compounds, rather than reactive corrosion products forming in neutral or acidic soils. Roman artifacts recovered near great engineering works often show superior preservation because of this alkaline halo effect created by centuries of groundwater interaction with limestone debris. Beyond passive factors, evidence suggests ancient cultures deliberately applied organic protective coatings. Archaeological residue analysis and fragmentary accounts indicate use of natural oils, rendered animal fats and waxes from beeswax or plant sources. These coatings required periodic reapplication, not permanent solutions, but maintenance regimes demonstrating awareness that corrosion required active management. Modern analysis has transformed ancient iron preservation from speculation into measurable fact. When researchers examine cross-sections of Roman nails under scanning electron microscopes, they observe grain structures markedly different from modern iron. The grains are fibrous and elongated, oriented along working axes, direct results of bloomery forging processes. This fibrous structure creates anisotropy in corrosion. Rust propagates preferentially along certain pathways naturally interrupted by slag inclusion distribution. The corrosion front fragments into isolated pockets rather than advancing uniformly, creating self-limiting corrosion profiles, preventing complete iron conversion to iron oxide. The protective patina itself, the dark surface characterizing well-preserved ancient iron, reveals under analysis to be a complex laminate of iron oxides and oxyhydroxides. outermost layers are frequently magnetite, a form far less permeable to oxygen and moisture than reddish ferric oxides, characterizing typical rust. This magnetite layer, sometimes just micrometers thick, remarkably blocks further corrosion effectively. The formation of this specific oxide phase appears favored by the slow, controlled corrosion environment created by iron's composition and environmental exposure. The ancient smiths remind us that resilience comes not from the newest technology or strongest barrier, but from understanding challenges we face, adapting to environment, and leveraging cumulative wisdom. Whether facing corrosion or modern challenges, perhaps the real lost tactic is the willingness to observe deeply and let nature itself become our teacher. If you found this exploration compelling, like this video, share it with those who appreciate history's hidden lessons, and subscribe to The Lost Tactician for more investigations into how our ancestors solved problems of survival and endurance. The tactics of the past await rediscovery. We'll see you next time.